theorem show that you can reduce it to something more concrete. But there's one very concrete object, the contribution of Choi in 70s, completely on a different subject, CSI algebra, commutative positive map. He discovered that there's one extremely powerful tool to check something is a so-called quantum channel. How? So you can easily implement it. Tell students to try that. It turns out that don't even worry about this FI. You just look at, if you are given a map, which is a linear map, you can do it already. So you can talk about the Choi matrix, which is extremely simple. If L is from n by n to n by n matrix, you just do record the basic complex unit, right? E11, you have a complex unit E12. Each of them, of course, L of the n by n matrix will be n by m, and you have n so many. So that is the famous Choi matrix associated with the linear map. It turns out that to do that, so that's what I wrote on the board, you have this block matrix, right? Each block is n by m, and you have n by n so many of them. It is a completely positive map, which means that it can be realized by such an equation. It's extremely simple. This large matrix is large, but checking it, just check it is positive semi-definite. This guy has no negative eigenvalue. Of course, automatically, it requires LE12 equal LE21 star. Those are basic structure of Hermitian matrix is required. But that's all you need to do. But don't forget, we want trace preserving for a quantum operation. But for a linear map, I already tell you all the elements of a basis. To check trace preserving, you only need to check trace preserving in each of them, then it is okay, right? Because in the future, how will you compute L of a xij? It's just xij times your L by linearity. You sum up all this Eij, right? So this elementary linear algebra. If I can check that for each of the E11 up to ENN, trace is preserved, that will guarantee for any matrix the trace will be preserved, but that is an open book. You look at this, LE11, is it trace 1? LE12, is it trace 0, and so on and so forth. That is the condition we need to check. So if you build a huge Mn by Mn matrix, which is positive semi-definite, and you check this piece as trace 1, trace 0, trace 0, trace 0, trace 0, trace 1, and so on and so forth, you get a quantum channel. Okay, let me repeat. Everyone here can produce a quantum channel. You just need to construct a Nm by Nm matrix, which is positive semi-definite, so that the block has trace 1, 1, and trace 0. Then you can recover your quantum channel. So two-way, I give you a map. Someone says, this is a quantum computer, try it. Then you try to put some quantum state, output quantum state to see whether it's satisfied. But behind, there is a quantum operation like that. If it fails, that is a fake quantum computer. Okay? The second application is to check a map. So that is the first application. The second application is when you want exactly our problem, when you want to construct a map, just construct something like that with all the requirements. What is our requirement? As I said, to make sure x go to y, that is the condition you want. If you want to check aj go to bj, you just check all of them. Many conditions, but they are simple. They are all linear conditions when you think about it. You want to take linear combination of those PRS, which is the block, which I want to put those to be our LEIJ, to satisfy this linear condition. So everything suddenly becomes linear, except one. This guy is positive semi-definite. So instead of using semi-definite programming, now I can play this game. Everyone knows that the positive semi-definite matrix form a cone, the self-dual cone. Okay, so this is the convex set. I have a lot of linear conditions like this, but they are linear. So all of them actually is a linear manifold, described by linear manifold. So this is convex, this is convex. Now I can do the projection. The only tricky thing is that how to find the projection of the matrix to the cone. A matrix to the linear space, just the usual Euclidean least square method. Okay? So, indeed, we finished this project by doing the following. I do a P0, just a scalar matrix here, so that is definitely remembered there. Then I can project it to the linear space or affine space using the least square standard algorithm. The only tricky thing is project it back to the cone. So after you project it, you get a matrix here. Then how to project it back? It turns out that very nice matrix theory tells you that if you have a n by n Hermitian matrix, everything takes place in the real space of Hermitian matrices. If the matrix has spectral decomposition like that, what is the nearest point in the positive semi-definite cone to your matrix? You simply throw away the negative eigenvalue. As simple as that, and it works. So we indeed use this algorithm to solve some moderate size problem that semi-definite program cannot handle. Okay. So we have the MATLAB program to do that. We can impose other requirements. For example, for minimum rank, we search for minimum rank, but we cannot prove that that is the minimum rank guy. Rank manifold is very difficult. It's not the linear manifold or the cone. So matrices with fixed rank or rank lower is a more complicated geometrical object. We can only try to project it to lower rank matrix and produce very good result, but no way to prove convergence. When we publish our paper, we actually use the Douglas-Roche for alternating method, which is slightly different. You do not project it to the two convex set. You actually project it to somewhere middle, and middle. If they overlap, then it will converge to this one. Otherwise, it will converge to a point that is near to both sets. At that time, when the technology at 2014, we do not even know it converge. It just performs so much better than the alternating projection method we proposed earlier. So we provide both algorithms and show people that it's a piece of cake to find a solution for a reasonable size problem. But I heard that in IQC this year, I talked to people, it is proven for two closed convex sets. This method actually is also convergent. No wonder that we have this successful implementation. Okay? So yeah, sometimes my pure math background is hard to believe. Sometimes you just have to do it for applied mathematics to do it, and it works, and later you'll find the reason. But when you, I don't know, I hope I'm not ruining the interest of pure math people. But I'm a pure mathematician, yeah. I truly still believe that beautiful theorem will justify everything. But sometimes when we want to build a machine, build a bridge, build the rocket to the moon, you got to use whatever available, and it worked, and then you have to use it. So that is this story. So I still have 10 or 15 minutes.
Is there a way to test for these two algorithms whether it's going to converge to zero or not?
Converge to
zero.
So
that you get an intersection or not. How do you decide that it's time to stop and they're not going to be?
In algorithm, we only give to the error, right? So we pay error bar. And to test whether it is satisfied the requirement, we just plug it there, right? So that all these conditions is easy to check. Once you find the object, this is your proposed quantum algorithm. You just put AI there to see whether you spit out BI, then we are happy.
But if you're not satisfying the conditions, then you wait until...
That is very good. Actually, in quantum computing, nothing is exact. So we can ask the question, if you cannot construct a quantum channel exactly fulfilling your requirement, how far away are they? Which means that maybe in your experiment design, you have to change the quantum state. The theory tells you that there's never a quantum operation transforming AI to BI. That's it. Okay, it's not the end of the quantum mechanical system, right? So the question is, when you build this machine, you better treat the two things to make sure that you find something that you can transform one to the other and use that in your computation or in your communication, right? So that is the reality, right? So question one, how to check? Yes, put it in if they suggest that is the quantum channel. If not, if the distance is really close, then the question is actually related to something I'm going to talk about, how to change the channel a little bit or change the state a little bit so that you get something which will be your result or do the best you can for that product. So. Okay, so what next? Here some follow-up problem. Again, mathematician never worry about solving all the problem, right? When the problem is solved, there are always some new problem. So here I will tell you that not all quantum channels are equal, right? So this is the basic channel. And unitary, we extend it to, it send the particular state In over n to Im over m. So the traits are both equal to 1. So traits preserving. So quote unquote unitary usually mean In go to In. But even different size, you can require this particular state go to this particular state. Okay? So this channel have more structure, more requirement. Even more is unitary similarity is the classical closed system quantum operation. If you have a system which will never happen, but if you indeed have a quantum system which will never interact with any other quantum system, then the only quantum operation is UXU star. Okay? Another type is the max unitary. You can combine several unitary channels by a probability factor. Okay, so in the lab, these are usually what people simulate. This one possible. 2 years ago, I heard some talk that they can do 2 unitary, mixed unitary channels. If it is mixed unitary, automatically, size will be the same, and then IN will go to IN, it will be unitary. So this different level of unitary, exactly like what I mentioned earlier. When you have a solution, now you want better solution. Better solution may mean you want require to be unitary, to be mixed unitary, or maybe even unitary. Okay?
So one question, what kind of quantum channel corresponds to taking a measurement? Is that like a map to a 1-by-1 matrix, or if you want to observe, take a measurement so everything collapses to one state?
Right, so that is what they call take everything to the garbage. So you can actually take any quantum state to one single thing. That is a simple map in mathematics. So you just, using physics notation, send rho to, you can fix any sigma. In particular, I can put it to be IN over N. But it is well known that if you want to construct a operation, send everything to a single state, sigma, you can use this simple formula. Right, so that is a completely trace-preserving completely positive map. Right, so you can always do that. And you talk about measurement operator, there is another thing. We can talk about that later. So there are other studies about the tomography problem, how you control the measurement and reconstruct the system or reconstruct the state. That is actually another interesting talk. Maybe next time I come here and we talk about that. But let me finish this quantum channel thing. So our trump card now as a mathematician, instead of looking at all those sophisticated formula of quantum channel, we can all talk about Choi matrix. General quantum operation, we have a general Choi matrix. Additional requirement only impose more condition on it. For example, I want unitary. What do I mean by unitary? Unitary simply means that Li equal to I. Then I just add this guy, add this guy, add this guy, add this guy. Then I get LV11. That is, by linearity, it's exactly Li. Then I can require it to be something, right? So you can actually impose all your requirement on the Choi matrix. And we can ask the question, can I construct a Choi matrix of special form, general form, or it is a unitary channel, or it is a mixed unitary channel, or it is a unitary channel by itself. Okay? Now, once you look at matrices, you can use all the theory about matrices in the convex set because the 3 sets are actually convex. These 3 sets, okay? And in optimization, if you have a convex set, you want to find something in the convex set or approximate it by something in the convex set, it is much, much better than a generic situation, right? And unitary channel, UAU star kinds of map is not so nice, but it is actually a set of extreme point of this guy. So there are also some geometrical meaning. So in the study, this matrix analysis result or property could be useful, okay? So we can ask the question, if I have a general, like earlier, we solve all the problems, we can find it using all kinds of methods to find a quantum channel. Can I find something even better? For example, a unitary channel. Can I find a mixed unitary channel to do it? So those will be 2 natural questions. After you see that, there will be different classes of quantum channel. Question 1 is really easy to answer because think about what we have done by the alternating projection method, right? Anyway, A1 up to AK go to B1 up to BK, I know how to solve. Unitary channel is no more than adding a A0 go to B0. So our whole method will be able to solve it. But if you want to check, it turned out the challenging thing, actually that was the last few weeks in IQC, I wrote a report, how to detect or check something can be done by a mixed unitary channel. Remember, mixed unitary channel is just U, XU star, U2, XU star, U3, XU star, do a probability mix of them. That is much more difficult. There are 2 sort of questions. I give you a channel. I even write down the Choi matrix. it is not so easy to check whether you can write as a mixed unitary channel. In the abstract sense, I give you a formula like that. But there are more than one way to represent this channel. So the question is, can I find suitable probability vector so that you can write? And you may even change this value, right? To fit our purpose, you may deliberately use more unitary matrices, more than our unitary matrix to do the job. I want a better structure, so I give up the number of operators here. I use more operators, but each of them are good. They are unitary, right? And then it would be waste if you already have a channel which is mixed unitary. You just do not see it, right? So first question is that, can you identify whether you can do it? And then the second question is that, suppose it is not, can I find something near to it? So these are two sub-questions you can ask. So to make the long story short, so it turns out that we can use some matrix theory to detect whether something is unitary, which is highly non-trivial. So I'm still working with Lockeris, the same old friend, in Waterloo, try to implement this algorithm, which require the following. You look at the big Choi matrix, decompose it in a certain way, and then construct some new matrices, and then you search for a solution T. You look at this one, again, I'm not telling you the solution, but reducing the problem to a computable problem to search for such a T. Okay? So if I can find such a T, then it is mixed unitary, otherwise it is not. Okay, in lieu of time, just get some idea. If you want, I will leave the file here. You can look at it later and solve my problem. But that is what we are doing here. And then we also have some theoretical result about the mixed unitary. I will highlight just one. For example, as I mentioned earlier, usually when you are given such an operator, a quantum channel, is it mixed unitary? Is a difficult question. Number two, even if it is mixed unitary, can I just use R unitary to do the job? No more. I don't want to increase the number of operators. Usually implementation will be more complicated. One thing quite surprised, even though it doesn't look very, very impressive. We know that if this is 1K, only one to begin with, then this guy has no choice but unitary, right? Because I require F1 star F1 to be identical. So if only one, that must be unitary. But we have proven that if you use 2, if you begin with 2, if it is not mixed unitary, then nothing we can do. But if it is, we can always use 2 to do that. Remember, these are huge matrices, which may be 10,000 by 10,000, right? And each of them can be very large. We are talking about a linear map on a very, very high dimension space. But if this representation allows 2, if it is mixed unitary, I don't need more than 2. 3, I don't think it is true, but yet to find the example to justify that. And there are some special kinds of quantum channel which are very useful in quantum information science, like the Schur channel, Hollywood-Werner channel, and so forth. We do some analysis on that, so that is some result. Let me end with something which you can, again, anyone is equal footing here can try to do that. It's exactly the question I asked earlier. Suppose I have a map, a linear map, which is actually, I listened in IQC by some other people. They are interested in doing exactly optimization problem related to frame. And put it in the context of quantum information science and find out that this becomes a very interesting question. Suppose you have a linear map, exactly like the earlier discussion. People produce a map, they may, because of measurement error, construction error, instead of producing a quantum channel, they prepare something which is not, but we know that it should be, which means that we have to see how close they are to the real thing. We can only guess. The maximum likelihood is that if it is close to some quantum channel here, then I would guess that, oh, the T you want to construct is this one. Or actually, I don't have something in mind. I just say, okay, starting from this apparatus, constructing this map, can I move it close to something which is a quantum channel, or a mixed unitary channel, or a unitary channel? This convex set, matrix set, think about the Choi matrix. I can always look at the Choi matrix of these sets, three of them are convex set, the other one is the extreme point, I can always ask a general Mn by Mn matrix, which is the Choi matrix of E. Can I get it close to any one of them? Do you have an efficient way to do it? Okay, so these are some new direction we want to study, and as I said, we can always look at the Choi matrix. In the construction, we want to find the minimum number of G to achieve the job. After we construct that Choi matrix, we have to go back and then look at G as small as possible. And some variation of the problem is that you do not find a T, make it close. You have to modify it from the given matrix transformation. To modify it, do a local modification. If it were not right, can I make it right by doing the local changes? You see the importance. Here, it means that you want a T, I just give you a T to represent your transformation, no restriction. Here is like plastic surgery, right? So I already give you some particular form. You are only allowed to perturb a little bit, can you still do my job? So these are two directions that are related to other problems related to our study. Yeah, I think my time is up. I hope that I described some problems, if not all the results, which are useful and interesting to you, and you can look at the problem and help me solve the problem. With that, I'll stop. Thank you.
Okay, any questions?
Answers. Any answers?
No answer to questions.
Yes.
So I have a couple of questions. So one question is in that linear map you have this parameter R. So it's a sum of R terms,
Right. Yes.
right? And you had these characterizations for the special cases of the commuting family and the rank one, where
That's
you
right.
reduced to a.
That's right.
But does the size of the linear program or the SDP, does it depend on R? I didn't.
No, it doesn't. It depends on K. A1 up to AK to B1 up to BK. K is so many states. Right. And after we construct after we solve it, we get the matrix D. Then D will tell me what is the minimum
Minimum R?
R we can get.
Oh,
Right.
really? Oh,
Yes.
I see.
And even back, well, actually, I should not say so. So by our construction, we can get up to so many R, we can do the job. But even at that point, can you find the really minimum R? I think it will still require some study. So you solve that following our tricks. It happens if only you have a D, and how to find the D so that it gives you the minimum R. We do not have an answer. We have some construction of D, which will certainly give you some decent size R to do that. Right.
But is it important for you to have small R?
Yes,
Or
at the beginning, because that is what they call the Krauss operator, is the number of things you need to simulate the quantum channel. So before I talk about mixed unitary, smaller is better. So you don't need to set up so many apparatus to realize that physically.
And the same holds for the semi-definite programs. So the solutions will determine the R.
Yes.
The different solutions
You
will
can
determine
impose
different
that,
Rs.
like I said, the alternating projection method. We try to search for this minimum R to do the job. Usually we get a very decent R, but no convergency proof. It's the optimal, which is very difficult to prove. Right.
And the other sort of other question is about problem one. So is there a particular norm with respect to?
Now, all norms are equivalent, so at the beginning, just find one close to it, I will be happy. But again, we can always ask further if people actually do the implementation. And they usually use the trace norm. Now, which is the sum of singular value. Now, for state, it doesn't matter, trace 1, and positive semi-definite trace norm 1. But for the Choi matrix, that matrix, the trace norm, it may vary. Yes.
Any other questions? Refreshments and, yeah, so normal refreshments in the normal place back in Whitehead. And let's thank them again. Thank you very much.
So I just leave the file here, okay? I just leave the file here. Okay?
So I will